So very good morning, my dear students. Welcome back. So we are continuing the alternating current chapter, and this is the chapter we are almost finished. All right, alternating current chapter we have almost finished. So I can say like two more classes left, right? Including this. After this, one more class. We are going to do that now. And last class we had discussed about LCR circuit in detail, right? LCR circuit in detail we have discussed. So this is an inductor and there is a capacitor. After that there is a resistor. All these three are connected to an alternating source. All these three are connected to an alternating source. So this alternating source EMF is E naught sine omega t here. So this is L and this is C and this is R. So what we have discussed by using the phasor diagram. So by using the concept called phasor diagram, right? So this is one method. So this is what the first method. The second method we have not discussed. So the second method I'll show you now. I'll introduce you now. By using this first method, what we have found. So we have found, so this E is equal to, what is that? Square root VR square plus VL minus VC whole square. Okay, VL minus VC whole square. From this E, what is this E actually? So this is what this E, understand? So that is this. Now here one more thing. So IRMS is equal to what we have found. So it is ERMS divided by impedance, the impedance of the complete circuit, the net resistance of this complete circuit. So from here we could also found the Z value is equal to square root R square plus XL minus XC whole square. So this is called inductor dominated circuit, right? So inductor dominated circuit. So that is what our assumption. Okay, inductor dominated circuit. Now, this is one method. In this method itself, by using the impedance triangle, we found tan phi is equal to, phi is what? Angle between, phi is this one. So angle between this E and current. So that is phi, net value of EMF and current. So this tan phi is equal to, as it is impedance, that means that is inductor dominated circuit, that is VL minus VC divided by VR. And this can also be written as XL minus XC divided by R. Alright. From here cos phi is also, cos phi, which is power factor, which is equal to cos phi is adjacent side by hypotenuse from this impedance triangle. Now, this is the first method, right? So there is a second method is also involved, my dear students here. So that second method is, see, let me write. The second method is analytical method. What is this? Analytical method. So from this analytical method, how we will be solving the similar equations and and before moving to that, so in the same concept only, we have found I is equal to I naught sine omega t minus phi, because in inductive dominating circuit, the current will be lagging. Remember, current will be lagging, whereas if it is capacitance dominated, current will be leading. Okay, so in analytical method, how we will solve? So there is a potential difference across these plus the potential difference across these. plus the potential difference across this, that must be equal to the applied potential of the circuit. Yes or no? So that I can write it as L into di by dt, the potential across the inductor plus potential across the capacitor plus potential across the resistor must be equal to your applied potential E naught sine omega t here. So this I can also write L into, so d by dt of I can write it as dq by dt plus q. This is q, as it is I'm writing q by v, plus again I is there, I can write it as dq by dt into r, which is equal to e naught sine omega t here. So now once again L into to d square q by dt square plus this is q by v plus, so dq by dt into r, which is equal to E naught sine omega t. So there is a differential equation we have got here, my dear students, right? So this differential equation, if you solve, you will get the solution of this solution of this differential equation. We get I is equal to I naught sine omega t minus phi if xl is greater than xc. Okay, so the solution, each and every differential equation will have its own solution, so that solution will be like, understand? So from here, what you will understand. So when you derive I is equal to I naught sine omega t minus phi, which is the similar equation from this phasor diagram concept. So you can also derive all those things. All these things you can also derive from this analytical method also. Okay, clear? So this is the concept of LCR circuit. Now, our major focus is about resonance condition. The major focus of ours now is resonance condition in this class. So mostly we are focusing on the resonance condition only, my dear students. What is the resonance condition? So this you might have you So what is the resonance condition here? What is the resonance condition here? When xc is equal to xl. So this will be 1 by omega c is equal to omega L. So what is that? So what I've told you, resonance frequency is 1 by 2 pi root LC. Sometimes questions also will be asked like this. They give L value and C value. So resonance frequency you can easily find out in terms of hertz. Okay. Clear? So remember this resonance condition. In resonance condition, we have Z is equal to square root R square plus XC minus XL whole square, right? So where XC is equal to XL, so then you have Z is equal to R. Okay. So which is the minimum resistance in LCR circuit. Minimum resistance in LCR circuit is possible when the Z is equal to R, so that is possible when XC is equal to XL. XC is equal to XL. Okay, clear? When XC is equal to XL, see, when XC value is equal to XL, so definitely voltage across the capacitor will be equal to voltage across the inductor. That is also possible. This is also the resonance condition, right? So no confusions. This is also the resonance condition, my dear children. All right. Now, let us solve some example problems before we move to the next topic. Example problems and some classwork questions, right? Just be right. Let me take another page. You can see me in a picture. Take this to here. Otherwise it will be destroyed. Okay, so let me have a red color here. Let's start. Let's take the first example question, right? So I have a few questions for you, and let us start. Fine. So this is my first question here. Okay. So there is a resistor and an inductor and a capacitor is placed. So it is connected to an AC source. This AC source EMF is given here clearly in the question, which is 50 root 2 sine omega t. 50 root 2 sine omega. It's given. And one more thing is given. So the potential across this is given as V2. What is that? Potential across the resistance. And potential across these two is given as V1. Okay, these two both together it is given as V. And you know this V1 is given in the question. V1, let's take V1 is 40 volt, and the question is to find V2. V2 is what? Potential across the resistance. Okay, and no other values are given, my dear students. Now, how to find this V2? Let's find a V2 here. How simple it is, let us see. What is this? To find V2, the potential across this, and we have the formula, right? So what is the formula we have? E is equal to, right? E is equal to square root of VR square plus VL minus VC whole square. So this is the formula you know already. Now, so what is this? Is it the net EMF? Net EMF of this complete circuit is equal to the RMS because it is AC current. So I can say this is ERMS. What is its ERMS? It is 50 because E naught is 50 root 2. ERMS is 50. 50 is equal to VR square. So that is our aim, to find VR square, potential difference across this resistance, plus VL minus VC. Yes, so this net potential between these two is given as V1. So what is that V1? So V1 is 40 square. Okay, I hope you understand the question. So let's square both sides. 50 square is equal to VR square plus 40 square. Okay, so this I can also write it as VR square is equal to 50 square minus 40 square, which is A square minus B square form. The answer is A plus B to A minus B. So that I can write 50 plus 40 into 50 minus 40. I can say it is 900. So when VR square is 900, VR is how much? It's 30 volt, my dear students. Clear? So the answer here, it is 30 volt. Like these questions will be asked. Ready? Are you ready to solve one more question? Let's solve one more question for you. Let's look at this example. Question is, there is a LCR circuit. Okay, there is LCR. And it is connected to the source EMF 10 sine 100 pi t minus pi by 6. Okay, and the current supply is given 2 sine 100 pi t plus pi by 2. Right, it's given like that. The question is, draw the impedance triangle. What is the question? Draw the impedance triangle. What do we need to find? You need to draw the impedance triangle. All right. So let's have a look at here impedance triangle. Let me draw an impedance triangle. Okay, so let's start. Impedance triangle. So what is the impedance triangle? So you know what is exactly the impedance triangle means. So this is value phi. Phi is what? Phase difference. Phi is what? Phase difference. So phase difference here. So between E and I. Okay, phase difference between E and I. So here what I can write. So this is called the phasor. Okay, this is called the phase and this is called the phase. Phase difference is this phase minus this phase. Again, I have to look. Oh, so many times I have told you phase difference is equal to phase of E minus phase of minus phase of I. So what is the phase of E here? So which is 100 pi t minus pi by 6. Okay, minus phase of I 100 pi t plus pi by 2. So sorry, it's 12. Sorry, it's 12. Okay, it's 12. So from here, if you solve, so you get it 100 pi t minus pi by 6 minus 100 pi t minus pi by 12. So this and this cancel here. So if you solve this, you get it as minus pi by 4. But phase as the formula of the phase difference mod phase of E minus phase of I. Okay, this is mod. So means you must take any positive which pi by 4 only. Okay, so this pi value is how much? Pi by 4. Okay, but that's not the end of the answer, right? That's not the end of the question. The question is draw the impedance triangle. We found pi only here. So here let's look at the concept of impedance triangle. In the impedance triangle, so this is R and this is Z, and let me say here, so this is, see my question is here, it is XC minus XL or XL minus XC, tell me now. So this is my question. XC minus XL or XL minus XC. Here you can see current is leading. Yes or no? Plus current is leading. Okay. So when current is leading, so definitely your circuit is capacitance dominated. So then this is not the thing. So this is the current. XC minus XL. So it doesn't make any difference here, but still you should understand each and every point of the concept. Okay, each and every point of the topic you should understand. So all right, so let us start. So your Z value. So what is the Z value here? My dear students, IRMS is equal to ERMS. I'm talking about the complete circuit, right? IRMS is equal to ERMS by Z. So what is IRMS here? So I is 2, IRMS is I naught. See, I naught is 2, IRMS is I naught by root 2. So let me write I naught by root 2, which is equal to ERMS. E naught by root 2, which is 10 by root 2. So divided by Z. Divided by Z, I can write it as so 1 by Z. Okay, clear? This is I naught. I naught is how much? Uh, I naught is how much? IRMS is I naught by root. I naught is 2, right? This is 2. So this root 2 cancels here. So and 2 5 here. So 5 by Z is equal to 1 and Z is equal to 5 ohm. Okay. So your Z value is 5, my dear students. 5. When this is 5, carefully see. When this is 5, you can see the other angle. So imagine if this is theta and this is also theta. If it is 5 and this side it is 5 cos phi. Okay, so that means this R is equal to phi cos phi. So R is equal to 5 cos pi. So 5 into cos pi by 4. So cos pi by 4, which is cos 45. It's 1 by root 2. So 5 by root 2 ohm. So this is 5 by root 2 ohm. So let me draw an impedance triangle here. That is our answer. Drawing the impedance triangle. So this is pi by 4, and this R value is 5 by root 2 ohm, and this is 5 ohm, and I hope you could solve this one. So what is this? So if it is sine, if it is cos, see for this phi, for this vector I've just resolved into two components. This is 5 cos and this is 5 sine phi. Okay, so your xc minus xl is equal to 5 into sine phi, which is 5 into sine sine pi by 4. Okay, so this is also 5 by root 2 ohm. Okay, 5 by root 2 ohm, right? So this is my impedance triangle. That's it. This is my impedance triangle. If you have any doubts, my dear students, if you have any doubts, you can do that. So you just use the Pythagoras theorem, and this square of this and this must be equal to this. That's one thing. And the second thing, we know the power factor, right? What is the power factor here? Power factor is equal to cos phi, which is equal to cos phi is equal to what? R by Z. Okay, so cos phi is 1 by root 2. Cos phi is what? 1 by root 2. So R by Z also you do. You must get 1 by root 2. So this is R and this is Z. So you do it 5 by root 2 by 5. So you get 5 cancel and 1 by root 2 you get it. Okay. Understand? So these are the two basic numericals we have solved. And are you ready to solve one more numerical? Ready? Just write in your WhatsApp, you are ready to learn one more numerical. Just write in your WhatsApp fast. Let's have a look at the another example. All right. Another example is this. Let's look at this. A series LCR circuit here also. So there is a series LCR. See, LCR can also be calculated and can also be connected in parallel. So that is not there for even JEE mains exam. Okay. So for even JEE mains exam, so the questions related to the parallel combination of this LCR is not there, right? So obviously for NEET also they are not there. Okay. Now, so given there is an LCR circuit, and here E is equal to, they gave as sine 10 sine 100 pi t minus pi by 6. Okay, and the current value they gave it as 2 sine, and similar to the previous question, 2 sine 100 pi t minus pi by 12 minus, it's plus, right? So it's plus here. So here, what is the average power dissipated? Right, average power dissipated is the question. And see, they have not asked, but I am asking you. So this is what is the element dominated in the circuit? LCR. See here, current is leading. Current is leading possible in the capacitive dominated circuit. Yes or no? Yes or no? Yes, right? So now, whatever it may be in LCR circuit, I have clearly given you power, average power consumed here is ERMS into IRMS into cos phi. Okay, so power average ERMS is what? So 10 by root 2, I naught by root 2, sorry, E naught by root 2 into IRMS, I naught by root 2 into cos pi by 4. Just now in the previous question, we found the phase difference, we get it as, right, phase difference, we get it as same pi by 4 only here. Okay, so then it is 20 by 2 into cos pi by 4, it's 1 by root 2. So the question, the answer is 10 by root 2 watt. So that is what the average power. All right. Let's have a look at one more question. Right. So many questions like this you can solve. So one more question. Let us have a look at it. So this one more question is based on the resonance frequency. See this question, they have given an inductance of coil 0.4 millihenry and which is connected to a capacitor whose capacitance is 400 picofarad. Okay, and to what wavelength is this circuit is tuned? Look at here, to what wavelength, to what wavelength is this circuit is tuned? That's a question. To what wavelength the circuit is tuned? And remember, when the tuning is happened, so that means there is a resonance condition is taken place. Resonance condition is taken place. Whenever there is a tuning is taken place, a resonance condition is taken. Okay, resonance condition is taken place. And very importantly, listen, very importantly here, what is the resonance condition and what is the tuning here? That's important. We have the resonance frequency f naught is equal to 1 by 2 pi root LC. We have the resonance frequency constant, right? What does it mean? Look at here, L and C. There is an inductor and the capacitor. So we have, let us take a concept of radio, where tuning will be there. So there will be a knob and we will be rotating it. At a particular point only, the channel will appear, right? So channel will be active. So imagine there is a radio where for this radio there is a tuner is there. Tuner means, so there is a knob which we will rotate. Rotating knob is there. Carefully see, a very important application of the LCR circuit I tell you this. So there is a radio for which tuner is there. Tuner means a knob which is rotating, right? So which is rotating. As you are rotating, you can change the channels. At a particular time, at a particular point of rotation only, you get a particular channel. Understand? So here. So this is the radio. Inside the radio, obviously, there is an LCR circuit takes place. So inside the radio, there is an inductor, capacitor, and resistor. So here what happens? You will be tuning it, right? When you are tuning it, your L and C values will be changing. Remember, when you are tuning, L and C values will be changing. When L and C values are changing, keep on changing, at a particular time, as the L and C values are changing at some particular time, so this complete right hand side equation is equal to f naught. For example, resonance frequency different for different channels, right? So for a particular channel, let us for a particular channel, for example, resonance frequency is some 440 hertz. Carefully see, right? So as you are changing your, see, you have f1 is 1 by 2 pi L into C, right? So by changing this L and C values keep on, so if you get at a particular point frequency is 440 hertz, so that is equal to your resonance frequency of that particular channel. What happens? You can of particular channel, right? So you can clearly listen to that channel. Otherwise, there will be noise. Otherwise, there will be noise. So for this channel, if you want this particular channel, your frequency must not to be less than f0, and your frequency must not be greater than f0, and your frequency must be equal to your frequency, in the sense this 1 by 2 pi root LC, this frequency must be equal to the actual channel frequency. So that is called the resonance condition. I hope you understand the situation, the practical application of the LCR circuit. Okay, so we will be, imagine a situation, we are just tuning the radio. If you are listening to one channel, if you tune little bit, the frequency will change. Whatever the changed frequency is there, if that is not matched with any of the channel which is already designed by the government of India, understand? So government of India will be giving each and every frequency, different frequencies for different channels. When you are tuning, as L and C values will be changing inside the radio at a particular time, at the particular tuning, because of your L and C values changing, so you will get one frequency. When that frequency matching to the channel frequency, and you get the clarity and the clear audio of the channel. Otherwise, no. The same thing was happened. So same thing was used to happen. The tuning theories, right? You might have observed or not. So nowadays we are using the remote and all. So previously there is a tuner for the TV, there's a tuner for the radio. So nowadays we are operating with the remotes, and nowadays we are operating FM radio in our mobile phone. There automatically it takes place. There also L and C, the same concept. The concept is same, but the changing this L and C is different. Previously we do with the tuners. Now the L and C values will be automatically changing with the help of electromagnetic waves. With the help of what? Electromagnetic waves. And this is our next chapter. After finishing alternating current, the last chapter of your second PUC is all electromagnetic waves. All right. Clear? Are you ready? Now, let's have a concept. This is called, okay. Come back to our concept. So that is what the resonance condition, and the circuit is tuned. When the circuit is tuned, you should understand this is given is the resonance condition. Now, L value is 0.4 millihenry and C value is given. Then you should find to what wavelength it is happening here. So first find the frequency. So what is the formula for frequency? F0 is equal to 1 by 2 into 3.14 into square root L into C. What is L? 0.4 into 10 raised to minus 3 Henry into C. C is what? 400 pico. Pico is 10 raised to minus 2 farad. Understand? So this value you get something, right? So F naught value is 10 raised to 7 divided by 6.28 into 6.28 into 6.28 into 4 hertz. That's a frequency. Okay. And see, in the final exam, so the questions will not be given this much lengthy. Okay. So simple values only you can solve it. So the question is finding the wavelength. We have V is equal to F lambda. From here, lambda is equal to V by F. V is what? V is the wave, which is an electromagnetic wave. Understand? So this is electromagnetic wave. So this V, whatever may be the wave, electromagnetic wave or microwave, so a visible ray, any kind. So they move with the speed of light only. So radio wave, anything, 3 into 10 raised to 8 by, so frequency given 10 raised to 7 by 6.28 into 4. So if you solve this, you get your wavelength as almost 753 meters. All right. Clear? So like this, the questions will be asked, right? At the end of the chapter, so I will give you an assignment. So now that is the reason I'm not going to give you any of class 1. Okay, class 1 questions also will be discussed in the, I'll be giving you in the next session. All right. Now, okay, my dear students. So let us continue the topic of LCR. LCR circuit is so much importance is there for your NEET exam. I've told you. We are taking the another page. Another page we are taking. Just a second. All right. Ready? Let's begin. So LCR circuit, another part, right? So in this part, we will be discussing about the concept called sharpness of resonance. You know about the resonance now. Sharpness of the resonance, bandwidth, and quality factor. All these three things will be depending on the concept what I've told you just now is tuning, right? Just now I've told you the concept of tuning, right? All the three will be depending on that. Ready? In a pure resistive circuit, my dear students, in a pure resistive circuit, what happens? We have resistance is equal to V by I. It is independent of the frequency. Yes or no? So this is independent of the frequency. So let me write this is resistance and this is frequency. So independent of the frequency. Now in a pure inductive circuit, we know XL is equal to omega into L, so which is equal to 2 pi f into L. So what happens in this case? In this case, so XL and frequency are directly proportional. So in case of pure capacitive circuit, my dear students, in case of pure capacitive circuit, what happens? So this is Xc is equal to 1 by omega c, so which is 1 by 2 pi f into c. What I can write, so this is f and this is xc. So this is the inversely proportional relationship. Now in LCR circuit, what happens? This is interesting. So in LCR circuit, what happens? In LCR circuit, we have this is the resistance, and this is the resistance. In LCR circuit, the resistance is Z, right? Z is equal to R square plus XL minus XC whole square. So if I consider this is inductive dominant circuit. So here, carefully, if you observe the situation, this is the frequency and this is your Z value. So there is an experimental graph is here. So this is an experimental graph. All right, see, there is a point here. So this is the point where frequency is F0. F0 is what? Resonance frequency. At resonance frequency, this is equal to this, and you get your Z is equal to R only. Understand? So this is what the experimental graph. So this is what. So Z value is minimum. Where the Z value is minimum? So I'm writing here. Is Z value is minimum, that is equal to R. In this case, so the LCR circuit is completely behaving as a pure resistive circuit. Okay. Now we know this already. What you know, what we know, right? Fine. So what we know, when Z is more, impedance is more, right? So what happens? The current will be less. So simple, right? Impedance is more, current will be less. So here, the same graph for the current. Look at here, same graph for the current. So this is I and this is frequency. And you can see, so these are the values, frequencies lesser than F naught, and these frequencies are greater than F naught. Okay. So exactly reverse. So when Z is minimum, so current will be maximum here. So now you can see the graph like this, right? So what is this? So this is current a maximum at frequency F naught, right? So this is F naught. I can also write it as omega naught. No confusion, right? Because the 2 pi F naught is only omega naught. Anyway, this 2 pi is constant. That is why 2 pi F naught I am just representing as omega. And this side, so this is F is less than F naught, and this side F values are greater than F naught. Okay, so at this I maximum, I is equal to V by R. Okay, so E by R is what? When I maximum, R is equal to Z only. So that Z is equal to R only. So this in a pure resistive circuit. Okay, clear? Now look at this. My dear students, there is a point. There is a point on y-axis where current value will be I maximum by root 2, right? 1 by root 2 times of maximum. So this is the point I'm writing it as omega 1 frequency, and this is the point I'm writing as omega 2 frequency, right? So so these are the points called these are the points I'm naming it as P1 and P2. So those are the points called half power points. What are those points? Half power points, where power is half and the current values are I maximum by root 2. Remember. And now this is the width delta omega, and this is the width delta omega. So total omega 1 minus omega 2 is called 2 delta omega. So this is called bandwidth, my dear students. What is it called? Bandwidth. All right. So what is it called? Bandwidth. Okay. Now omega naught divided by 2 delta omega. So that is called the sharpness of resonance. What is this? Sharpness of resonance. Okay, sharpness of resonance. So this is sharpness of resonance, and this is omega naught by 2 delta omega. Okay, clear? So what is sharpness of resonance? I'll tell you. See here, when delta W or this bandwidth is less. Okay, so when your bandwidth is less and the sharpness is more. Sharpness will be more. How? You can see this graph. So from this graph, what I can draw, see here. So if you take a graph here, so this is frequency and this is I. So this graph I'm just redrawing by decreasing the length delta W length, right? So this graph will be like this. So see here. So when this delta W value is less, what happens? So the curve becomes very sharper, right? So previously it was like this. So that is called when delta omega is less, sharpness is more. That's called the sharpness of resonance. Okay, clear? And this sharpness of resonance can also be written as omega naught L by R. What is that? Omega naught L by R. So which is called quality factor. What is this? Quality factor. Same thing. Quality factor expression and the sharpness of resonance expression is same. So from here, omega naught by 2 delta omega is equal to omega naught L by R. Sharpness of resonance and the quality factor. Okay. Clear? So this is the concept of LCR circuit and what is bandwidth and what is sharpness of resonance, all the things in detailed analysis we have done. And let's see how the questions will be asked, my dear students. Here itself, here itself. All right, here itself how the questions will be asked. Question for you is, there is an LCR circuit, right? So there is an LCR circuit is given where L is equal to 2 Henry and capacitance is given as 32 microfarad. Okay, and resistance is given as 10 ohm. So now the question is finding quality factor. What is that? Find the quality factor. So simple. Quality factor formula I told you, omega naught L by R. We have L, we have R. Omega naught we don't have. Okay, so it's an interesting thing. So we have omega naught L, sorry, we have L, we have R, omega naught we don't have. So that is why Q is equal to omega naught is 2 pi F naught into L by R. Okay, so from here, so we know F naught is equal to what? 1 by 2 pi root LC. So 2 pi F naught is what? 1 by root LC. Okay, so this I can write 1 by root LC into L by R. Okay, so this I can also write it as root L by root C into 1 by R. So finally 1 by R into root L by C. So you can write, right? So Q, you know, sorry, Q we need to find out. R is there, L is there, C is there. You do it and tell me the answer. Show me the answer now. This is the class you are just write the answer. All right, my dear students, and we will be discussing LC oscillations topic in our next class. What is that? LC oscillations and transformer. LC oscillations and transformer. All right, so that will be the last class of the chapter. Thank you so much. All the very best for your assignment.